Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on numerical integration in Java. So far we looked at the simple methods such as rectangle approximation, trapezoid, symptom, and we also looked at how to implement them recursively. Now let's go and continue to more advanced concepts in numerical integration and advanced methods. One of them is Newton-Cotes method. And what do we mean by that? So sometimes we only know the values of the function at some given points, which are normally uniformly distributed over an interval, okay? This means that we don't have the expression of the function, but we have the values of the function that at some equally spaced points. Now, when does this happen? One use case or one case that this happens is, let's say you have a signal coming into your electrical circuit, and then you sample it at some rate, let's say 10 kilohertz, 20 kilohertz. It means every 10 millisecond or every 1 millisecond you're taking a sample of the signal, which means you're taking a value of the function, right? And sampling is normally a uniform thing, so the distance or the time between two sampling points is equal. It's always the same, it's constant. That's why you have a signal, you have the values of the signal at some points that are equally spaced over time. Now let's say you have sampled the signal, now you want to integrate it. So how do you do that? One approach is Newton-Cotes, and it says, okay, remember the Simpson's method, what we did in each small interval? Now extend that to the entire interval, right? So instead of interpolating the function in a small interval with a quadratic polynomial, what you're going to do is just interpolate the function based on the number of points that you have and a quadratic polynomial of that degree. So if I have n intervals, which mean I have, if I have n intervals, it means I have n plus 1 points of the function, right? And that gives me n plus 1 degrees of freedom. Therefore, I can fit those points to a polynomial of degree n, okay, for polynomial, because a polynomial of degree n has n plus 1 coefficients, which are unknown, and we know them after doing the fitting. And how do we find these polynomials? These are exactly the Lagrange polynomials, which we discussed here in Simpson's method. So Newton-Cotes says, okay, try to interpolate the function using a polynomial of degree n based on the endpoints that you have. It's Lagrange polynomial. And this Lagrange polynomial in each so basically Lagrange polynomial is the sum of the values of the function times the Lagrange term, right? So the whole summation is called the Lagrange polynomial, but then each term here, Li, is a Lagrange, let's call it Lagrange term, for example. So the whole summation is the Lagrange polynomial, because each one of these Li's has this property that if I plug in xi, so Li of xi is 1, Li of xj, which j is not equal to 1, is not equal to I, is 0. So Li of xj is 0, Li of xi is 1, right? So, okay. And then we said that, okay, now if this function is approximating my actual function, then the integration is also an approximation. And then because Li's are polynomials, we know exactly how to calculate them. Therefore, what we end up, and if you see in this summation that fxi is a number, integral of Li is also a number, all right? So our integration of f of x over a and b becomes a summation of some wi's, which we call them Newton-Cotes weights. So this is the constant of weights, times f of xi, the value of the function at xi. Now, in the original definition of Simpson's Riemann summation, we had f of xi times delta x. So we were evaluating the value of the function at some point inside in each interval, and then multiplying it by the length of the interval. Now the difference here is that we calculate the value of the function times some weights, which are called Newton-Cotes weights, right? And then these weights are the integral of the Lagrange terms, right? And this gives a better approximation of the function, of the integration, instead of having just simply f of xi times delta x, all right? Now, if let's just assume that we want to integrate over a and b, right? So if I use only 2 points a and b, I end up with so if I use only 1 point, the degree of polynomial is 0, which means I'm interpolating with a constant polynomial, and that constant polynomial is basically 1, right? It's basically 1, and therefore what we end up with, so actually the constant polynomial is 1, and then we end up with the rectangle method. So if we use 2 points, the start point and end point, a f of a, b f of b, so what happens is that we end up with the trapezoid rule. If we use 3 points, we end up with Simpson's rule. If we use again 3 points, if we use basically, so trapezoid is first degree, Simpson is second degree, and then Simpson's 3/8 rule is also the degree 3, and then we have also Boole's rule, which is interpolation with a 4th order polynomial, all right? And this approximation is accurate when the interval is small. If the interval is large, what we do, we use the fact that, okay, over each small interval, I can do this approximation and then sum them up to get the value of the function, right? The value of the integral of the function. And so we can make this as accurate as we want by increasing the degree of the polynomial. And again, this whole pertains to a uniform partitioning, all right? So this whole idea of Newton-Cotes rule and the trapezoid, Simpson rules, Boole's rule, all of these that are derived from this Newton-Cotes rule are for uniform partitioning. Now the question is uniform partitioning is actually the optimal case? And the answer is no. Uniform partitioning is not the case, and that leads us to the next and the widely used method called Gaussian Quadrature or Gauss Quadrature method, all right? And the idea is that we want to generalize numerical approximation of an integral. So far we saw that the simple definition of integral is the Riemann sum, which is the value, the sum of the f of xi times delta x. And then we see that the recurring theme in making the numerical integration more and more accurate through different methods was that we started with the definition of the sum, Riemann sum, which is basically based on the fact that it approximates the function with a constant polynomial of degree 0 in each subinterval. The problem was that the error was order delta, so I need to have a lot of subintervals. And then if we want to improve the accuracy, we said that we can go to trapezoid, and it's based on the interpolating of the function by linear polynomial degree 1. It gives us an error of delta squared, and it gives the exact result for first degree polynomials. And the Simpson idea was we wanted to have exact result for the second degree polynomials in each subinterval and of course in the entire interval, and the error improved to delta 4, all right? And then the Newton codes was, okay, I can generalize all these ideas with Newton codes for uniform partitioning. Remember, those were for uniform partitioning so far. And then we saw that, okay, I don't need to actually use uniform partitioning for these ideas, rectangle, trapezoid, Simpson, right? Because regardless of how the partitions are made, I can do this kind of interpolation in each subinterval. Now what we are going to say is that let's forget about uniform partitioning. What I want is I want to be able to write this integral f of x dx from a to b as a summation. If I have n partitions, I from 1 to n or 0 to n or 0 to n minus 1 of the values of the function at some points times some weight coefficients, which are called Gaussian Quadrature weights, and the Excise are Gaussian Quadrature points. All right. So I want to pretty much be able to approximate the integral in this form, and we already saw that in Newton codes we can use uniform partitioning and do this kind of this thing, right? This kind of writing. But let's generalize it. Is that okay? We looked at the 0th order, first degree and second degree polynomials. If I want to choose this and I don't want to have any uniform partitioning or anything, I have 2n unknowns, right? If I have n terms in this summation, I have n w's and n x, which I have to find. So 2n unknown parameters here, all right? And let's set the condition is that I want this approximation, this approach, to be exact for polynomials of degree 0 to degree 2n minus 1. So I want this approximation to actually give me the exact result for 2n polynomials. And if I set this approximation to equality by plugging in the x to the 0, x to the 1, x to the 2 on these terms, I end up with 2n equations with 2n unknowns. So I should be able to uniquely determine wi's and xi's, all right? Now, why is this a good way of doing the approximation of any function? Because of Taylor expansion, right? And that was the whole idea between all these trapezoid, rectangle, and Simpson method, right? So the whole idea is, okay, I want to be able to write the integral in this way, in this fashion, with some weights and some points. And then the Gauss-Legendre quadrature rule. So this was the general definition of the quadrature rule, right? Or the Gauss quadrature. This is a general definition. For Gauss-Legendre quadrature, we have the constraint that the integral should be accurate for all these 2n polynomials over the interval of -1 to 1. So that's because Legendre polynomials, which we will see later, only are defined from -1 to 1, all right? So the Gauss-Legendre rule is that, okay, this integral should be accurate for intervals of -1 to 1. And then what if I want to actually calculate the integral from a to b? We can use a linear mapping from -1 to 1 to any interval a and b. So if x is in the -1 to 1 interval, I can map it to any point in the AB using a uniform mapping, b minus a over 2 times x plus b plus a over 2. So if I put x to -1 here, it gives me the start point, which is a. If I put 1 here, it gives me the end point, which is b. And it's a 1-to-1 linear mapping or uniform mapping, and the integral of a and b f of x dx becomes b minus a over 2 integral to -1-to-1 f of this whole thing dx. And this whole thing can be viewed as a so this whole f of something can be viewed as a g of x function, right? So basically integral of -1-to-1 g of x dx. And g of x is just f of b minus a over 2x plus b plus a over 2, okay? So if I'm able to integrate any function from -1 to 1, and I'm able to approximate it with some weights and points, which I need to find, then I can calculate or approximate the integral from over any interval a to b. I can first transform f into g using this mapping and then find the integral of g over minus 1 to 1 and then multiply it by b minus a over 2. Alright, this gives me this approximation based on the Gauss-Legendre quadrature rule, right? And then now the question is, first of all, in order to do this, we have to find wi's and xi's, right? And the way we find it, again, we form a 2n equations, a set of 2n equations based on the condition is that we need to get the exact result. This approximation must yield in exact equality for polynomials x0, x1, x2 to x to 2n minus 1. So 2n polynomials from degree 0 to degree 2n minus 1. And it gives us 2n equations, which helps us to uniquely determine the wi's and xi's. But the problem here is that these are nonlinear equations because the values, the parameters or the variables are w and x. So it's not easy to solve it, but luckily it's actually possible to solve it and get the closed form relations for the w and x. And the way it happens is that with the notion that the fact that we choose minus 1 to 1 to be able to establish in this equality is very good, because then every odd degree, x1, x3, x5, etc. automatically results in 0 for a minus 1 to 1 integration, right? Because it's an odd function and the interval is symmetric, so it definitely results in 0. And that helps us to be able to solve the equations in a closed form way. And the final result is this: the weight coefficients are 2 over 1 minus xi squared times p prime of order n xi squared, and p of n is the nth order polynomial, Legendre polynomial. All right, and these polynomials are defined over the minus 1 to 1 interval. So wi, we are able to find wi's in terms of the xi's. And how do we find xi's? Xi's are actually, the xi is actually the ith root of Pn, and which is the nth order Legendre polynomial. And the thing is that wi is equal to this expression as long as we do this normalization over for the Legendre polynomial. And the normalization is that the nth degree Legendre at x equal 1 should be 1. This is the normalization. When we do this normalization, wi is equal to this term, 2 over 1 minus xi squared p prime n xi squared. So we have to find the Legendre polynomial, normalize it, and when we normalize it, then what happens here is that the xi is the ith root of the Pn. Actually, the xi doesn't depend on this normalization. Xi's are always the ith roots of the Legendre polynomials, and the weights are calculated based on the xi's. Okay? And in order to be able to find wi's based on this expression, we have to normalize the Legendre polynomial. Now, this table is from Wikipedia, and this shows us based on the number of points or the partitions that we choose. Let's say if I want to only 1 point, then the point, the xi is 0. The approximate value of xi is also 0. And the weight is 2. And that's because when n is 1, we are basically approximating this with a constant function. And the value of the function is obviously, logically, it should be at the middle of the interval, which is 0. And if we're setting the constant approximation, wi should be the length of the interval, which is 1 minus 1, which is 2. So with one point approximation, we end up with 2 times f of 0, the midpoint. That's why when the degree is 1, the Gauss-Legendre quadrature is just 0 for the center, 2 for the weight, all right? But if we have 2 endpoints, 2 points, x1 and x2, for example, then we have to use 3 polynomials, 1x, x squared. And it's actually an easy case to write it down, write the 3 equations, and write the 4 equations, right? x0, x1, x2, and x3. We have 4 equations, and it's possible to calculate the exact solutions by hand, just using the math, right? Solving the 4 equations. And you end up with the fact that the xi, x1, and x2 are plus minus 1 over square root of 3, and wi's are 1, the weights are 1. So if I want to approximate this function, this integral with 2 points, I have 1 times f, the value of the function at 1 over square root of 3, plus 1 times the value of the function at minus 1 over square root of 3, all right? And etc. If n is 3, we have the roots of the 3rd degree Legendre polynomial, and the weights are calculated from these 4, 5, all right? And then the next thing is that we can just use this table and go ahead and implement it in Java. Let's say instead of doing this for the entire interval, if the interval is large, we divide it into sub-intervals, and in each sub-interval I calculate the for example this integral using this mapping, right? So the first thing I need to do, I need to create this mapping. So let's go here to the Eclipse, and in the integral 1D, what I'm going to do here, I create a private method, Gauss-Legendre mapping double x. So the mapping is that what happens here is that whenever I do this mapping, let's call it interval mapping, and here it returns that let's say double start, double n, double x. It returns that n minus start over 2 times x plus n plus start over 2. Okay, so this maps from minus 1 to 1 to any interval start end. Okay, now we obviously we can do the reverse of this, private double Gauss-Legendre inverse interval mapping, and double start, double end, and double x. And here we do return. Basically what happens here is that we have 2 divided by n minus start times x minus n plus start over 2.0. all right, so if I set the x to end, I have n minus start over 2 times this, it returns 1. If I set the x to the start point, I get minus n minus n start over 2 times this, which is minus 1. So this basically what happens here, this does the mapping from start end to minus 1 and 1. all right, and then let's do a private double Gauss-Legendre function mapping, double start, double end, double x. So what we want to do, we want to map the function from start to end interval to the return t goes to, so we want to return an integral function 1D, but what we want is to map it to the -1 to 1 interval. So we get the func dot value Alright, so let's call this integral 1D, and then the return type is func dot value functional integral function 1D. Alright, and then here we map x to so Gauss-Legendre, this should be Gauss. So Gauss-Legendre interval inverse interval mapping start end. All right, and let's remove this and t. Okay, so basically what happens here is that we create a function, so t is between so t is in start end, okay, interval, and then we use the inverse interval mapping to map it to -1 to 1 and create an integral function 1D, an functional interface that represents our basically, if I go back here, our g of x here. All right, it's our g of x. So g of x is the value of f at this point. And then what we do here, we calculate the integral of this at -1 to 1, so private basically double Gauss-Legendre, let's call this -1 to 1 interval double start double end. So if I want to calculate this, I create a basically integral function 1D, let's say mapped, let's call this mapped func is I don't know why I'm making a mistake here, a typo. Gauss function mapping start end. Okay, and then let's also do the create another one, function mapping, inverse function mapping. Inverse function mapping, we have to use the we have to use the interval. So here t is in -1 or 1, okay? And so what we are going to do Here we're creating an integral function 1D, which is our mapped function, and then the next thing is to double, these are our weights, and double, these are our points, Excise, alright, and then double sum equals 0, and then let's make this public. Gauss-Legendre, let's say 3 points. So we want to implement the 3-point Gauss-Legendre, and the weights for the 3 points are let's see, the weights for the 3 points are 0 and plus minus square root of 3 over 5, which is 0.774597. Okay, so the weights are, so the points are 0 and 0.774597 and the negative of this. So these are my points, and then the weights are 8 over 9 and 5 over 9. 8 over 9 for 0, and 5 over 9 okay, and then sum is basically we write an int for int I equals 0, I less than points dot length I plus plus sum plus equals what we are going to do, we are going to get the weights at I times the value of the mapped function at basically the points I. Alright, so this is our quadrature rule, and then we return sum. Okay, so let's see what we did here. And so we are creating a mapping of the -1 to 1 to a star to n. Why are we going through this? Because the Gauss quadrature, so basically the closed form equation for the weights and the points are based on the fact that the original Gauss-Legendre are based on the Legendre polynomial if and only if the integral limits are from -1 to 1. So if we are starting with this problem, then we can find the weights and the points with closed form solutions, right? And then we need to solve the problem of integrating from a to b, and for that we use this mapping that a to b f of x d of x is b minus a over 2 times this mapping, this integral of g of x. All right, so what we are given is the function over a and b, so we want to map it to a function which is defined or equivalent to our function over -1 to 1. So we use this g of x. G of x is f of this mapping. Okay, now in this mapping, this x here is between -1 to 1, this x is between a and b. So what we need to do, we need to do the inverse mapping, right? So I want to calculate this first, so I assume that my x is between -1 to 1. If it's the case, then g of x is f of this term. So here in the Gauss-Legendre function mapping, what we are going to assume is that we're calculating the value of the function, assuming that t is between actually this, I think this should be reversed, right? -1 to 1, and then this should return the map. Yes, because the interval mapping maps from -1 to 1 to a star to end, and then the function is defined over, oh yes, And the inverse mapping, we have to have inverse interval mapping. Okay, so our mapped function is here is t is in -1 to 1. So Gauss-Legendre function mapping, which is the function calculated at this mapped interval such that this variable is between -1 to 1. Okay, and then we sum the we get the value of the map function at the points, quadrature points, which is defined for a 3-point quadrature rule. So we are doing a 3-point quadrature rule, or Gauss quadrature rule, Gauss-Legendre quadrature rule. The weights points, they have closed form solution as long as our function is defined between -1 or 1, right? So this summation, weights times the value of the map function at these points, it gives us the integral of this mapped function over -1 to 1. All right, and then if we because of this, the fact that we map the interval, it's equivalent to mapping the calculating the integral of the function over over the entire interval start to end. Now the problem is that if the interval is long, is a large interval, the 3-point rule is not going to give you an accurate result, right? So let's go and test it first. In test 4, we had different types of methods. And let's say we want to do t cubed, for example, and Simpson recursive. So I'm going to remove these. Okay, I'm going to add the Gauss, and in the Gauss, I'm going to call the Gauss-Legendre polynomial 3-point. So Gauss 3-point approximation. $32. So we are off by a factor of 2. Oh, that's because, okay, sorry. That's because this sum gives the integral. Okay, so when we did the mapping, we mapped it, but this sum is the integral over basically -1 to 1. And if you recall here, we had this factor b minus a over 2, right? So we have to scale the calculated integral by this factor. So I have to return this sum times basically end minus start over 2.0. Yeah, and the thing here is that we didn't do much. It's extremely simple, only 3 points, and we're getting almost exact result, and it should be, because the 3-point is supposed to be accurate up to polynomials of degree 5, right, to n minus 1. So T3, T4, T5, these all should, the Gauss quadrature should give me exact results. 682. Okay. Simpson returns 682.666, and then maybe let's also try the exact here. If it's T5, I should have n to the 6th power minus start to the 6th power divided by 5, 6. So the exact is 682.666,666, which is basically Simpson. Now the Gauss, in the Gauss quadrature, as you can see, it gives us 6672. And the question is, why is that is not giving us exact? Because we used the exact results for weight, but we didn't use the exact results for the points, right? We used only 6-digit, 6-decimal approximation. So the exact points or the exact values are square root of 3/5. So let's use those. Instead of having these, I use math dot 3/5 and the negative of this. Okay, now I'm using the exact values for the quadrature points, and let's try it again. Yes, now it gives us the exact result, 682.66666. Okay, so this is a 5-point or 3-point quadrature, so we can increase it to, for example, 5-point. Instead of 3-point, we go 5 points, and 3.5 point. Everything is the same, the mapping is the same, and then the summation is the same, and then when we integrate over -1 to 1, we scale it back. The only thing that changes is the weights and the points. That's the only thing that changes. Okay, and for the 5th degree, we have 0, 1/3 square root of 5 minus 2 square root of 10/7, and these are the weights. So it's a little bit hard to write, but you get the picture. So one of the points is 0, the other point is 1/3 square root of 5. So 1/3 times math dot square root of 5 minus math dot square root of 10/7. Okay, 5 minus 2 times math square root of 10/7. And that's one of the weights. The other weight is the negative of this one. Okay, and there are 2 more weights that we can write them down here, but there are 2 more points. And then let's look at the weights. For 0, the weight is 128, 225. So 128 divided by 225. For the next points, 1/3, 5 minus 2 square root of 10/7, 322. Okay, let's add the other points. 1/3 square root of 5 plus 2 square root of 10/7. Square root of 5 minus 2 10/7. The other 2 points are 1/3 square root of 5 plus 2 times square root of 10/7. And the next point is basically the negative of this one. Okay, let me just go full screen. Alright, so we have 5 points, and we need to have 5 weights, and the weight for the other 2 is 322 13 over, okay, so 322 plus 13 times square root of something over something, right? How much was this? 13 square root of 70 over 900. 70 over 900. And the weights are the same, right? 322, 13 square root of 70 over 900. For these two, And for the next ones, we have 322 minus 13 square root of 70 over 900. So 322 13 square root of 70 over 900. We just use a minus sign. 322 minus 13, and the next weight is also the same. Okay, and this is basically a similar thing. So let's go here to our test, and let's do Gauss 2, Gauss-Legendre 5 point, and then Gauss 5 point, Gauss 2. This also should give us exact results, but it doesn't. So the 5 point fails, and the question is, why is it we're getting error here? And let's check the weights. 322 minus, and the roots are 0, 1 over 3, square root of 5 minus 2, square root of 10 over 7. Uh, 322 plus 13 square root of 70 over 900. We take the weight and then we use the map function over 900 here, plus plus minus minus 1 over 3, 5 minus, oh sorry, so the last weight is minus. Okay, yeah, so the points come in opposite signs. So 1 over 3 square root of 5 minus 2 times square root of 10 over 7. The next one is negative of that. The next one has a square root of 5 plus, and the last one is minus 1 over 3 square root of 5 plus. Okay, so let's go to our test. Yes, now we get the 5 point, the exact result. And keep in mind that with 5 point, and again, this doesn't have any complications or any burden, because we're calculating the original function at 5 points. Remember, we're only calculating at 5 points. And so only 5 evaluations, nothing else. The weights are given, the points are given. The only thing that we need, 5 evaluation on the function and do the summation. That's it. So that's the power of quadrature, because the weights and the points are predefined. And then we see that up to the polynomials of order. So with 5 points, we have to be able to get ninth order polynomials. We should be able to exact result. And that's a very powerful thing. And then the main problem here is that with quadrature, if the interval gets very large and the error of the quadrature scales up linearly, that's because of the factor b minus a over 2. So when we are integrating over the minus 1 to 1 of this map function, the error is constant, because that's the definition, that's how the Gauss quadrature works. The error is constant. But then the error of this a to b integral is the error of minus 1 to 1 integral times b minus a over 2. So the error scales up linearly with the length of the interval. That's the problem with Gauss quadrature. The solution is to divide the original interval into sub-intervals. But we don't need to do, for example, 100 sub-intervals. We can do like 10 or 20, or based on sub-stop criteria or the error tolerance that we want. So here I'm putting 40, and let's see. And the thing is that here, because the function is polynomial, we should always get the exact result. Let's change it to math.sine of x or sine of t. And let's keep the 4 So we're integrating from 0 to 4. The exact, okay, so the exact result is, never mind. So symptom is 1.85777, and the 3-point quadratures, you see it starts to lose accuracy. It's 1.888, which we know that the exact result is 1.8577. So we have quite some error here. The 5-point quadrature turns out to be very close to the exact result, 1.85778. Okay, so if we want to increase the accuracy, we need to increase the number of points of the quadrature. But after a while, it becomes it adds more overhead in terms of the calculation. So there is a trade-off between how many points we use for the quadrature, Gauss quadrature, and how many sub-intervals we divide the original interval, okay, into. So if I put 40 here, for example, the recursions, let's also comment out the recursions. Again, I don't recommend recursive approach for integration because there is really no point to that. And as you can see, all of this approximation, especially the trapezoid, Simpson, and the center approximation, center rectangle, they give a pretty decent result, but the Gauss 3-point or 5-point, there is just pretty much garbage. And that's why if the interval is very large, it just loses its accuracy, 3-point or 5-point. Okay, so in the next lectures, we look into ways of increasing the number of points, because we cannot just go to a table and try to look them up. We have to be able to calculate them. And then also the other approach is to divide the original interval into several sub-intervals and use a low-point Gauss quadrature for each sub-interval. Thank you for watching, and I'll see you in the next video.